All right, so from last class, we looked at this binomial distribution example. We looked at using Binomial PDF, and at the end of the example, I introduced to you Binomial Cdf, a cumulative distribution, and what it does is it counts up all the frequencies up to a certain amount and adds them up. So you've got your probability distribution chart. So let's see what kind of example here. We're flipping coins. So here I'm going to make a probability distribution chart. There's x, the probability that x equals x, and if you flip that coin 3 times, 3 trials, you could get 0, 1, 2, or 3 heads. And if you did your probability distribution chart, we could figure out the probabilities of each of these. And I think we did this one already. I think the numbers were 1/8, 3/8, 3/8, and 1/8. With the cumulative distribution, what it looks like is what would happen if you had added these up. So 1, not having any would still be 1/8, but then at 1 it would add up the 1 and the 0, so this would now be at 4/8. At the 2 it would add up the 0, the 1, and the 2, so this will already be at 7/8. And once you get to the 3, it'll add them all up all together. So when we do binomial CDF of 3.5 and 2, it's adding up these 3 together, and that's the number that it's producing for you. Now, the cumulative distribution can be nice if you're wanting to find questions like, what are the chances that you will get at least this many? And then you want to do more than and figure out, just like we did in that previous question, where we wanted to find at least a certain amount. Binomial CDF is in the same place on your graphing calculator under distribution, second vars, as binomial PDF. And so there'll be a couple questions that we can do for that. So if you were, for example, this example here at the bottom says you have 6 trials, the probability of success is 0.3. And if you want to figure out what is the probability that something is greater than or equal to 2. Now, if you made your distribution chart for 6 trials, and you could have a success or failure, it's going to go 0, 1, 2, 3, 4, 5, 6. There's going to be a lot of them in 6 trials. In 6 trials, your probability distribution chart will have 7 things. And if you want to figure out the probability that it's greater than or equal to 2, what you're looking for is this one, plus this one, plus this one, plus this one. You're wanting to add all of those up. And so you could do that. You could do binom PDF of 6, 0.3, and 3, 6, 0.3, and 4, 6, 0.3, and 5, 6, 0.3, and 6, and add all 4 of those up, and you will get the probability that x would be bigger than or equal to 2. But if you use the cumulative frequency, what this does, greater than or equal to 2, you'd also have to circle this one. There we go. What the cumulative frequency does is it says we will add up to a certain number of trials. So the fact that there is a 1 here means that they will add those 2 up for you. If there was a 2 there, they would add the 0, the 1, and the 2 up for you. And so if you wanted to find all of those red circles, instead of doing 5 separate cases, you could just do 100% minus the cumulative frequency of those first 2 added up. Does that make sense? Sort of? Okay. So I'd like you to read through this problem. I'd like you to try and set up what you would put into your formula, what you would put into your calculator. Give you a couple minutes head start on it. As far as setting this one up, this is a binomial distribution because there's a success or a failure. The plant either grows or it doesn't grow. So one of the things that you're going to have to start getting sort of good at is recognizing when something is a type of question and being able to read this one and see there's a certain number of trials and I either have a success or a failure. So that's going to set this up as a binomial distribution. We have 10 trials and our probability of success is 0.8. Then if you want to find the chances that all of them germinate, you can use Binomial PDF. You'd put in 10 for your trials, 0.8 for your probability, and you want to find in particular what are the chances that all 10 germinate. So there's about a 10.7% chance, rounded to 3 sig figs. You could have also done this one using the formula. So using the formula, and this formula in the green there, that formula is on your formula sheet. It would be 10 choose 10 because we want to find all 10 germinated. Your probability of success has to happen 10 times. Your probability of failure doesn't happen at all. And that also gives you the exact same number. What is the probability that only 3 seeds will not germinate? Well, here's using the formula. For this one, you want 7 to germinate, so the 0.8 would happen 7 times. The failure would happen 3 times. And so it's good to get used to the formula as well, so you could sort of use them interchangeably. If you wanted to write it out in the formula form, or if you wanted to write it out with the binomial PDF. I find that these questions are sometimes hard mathematically because if you're using your calculator's program and you write this out, when you get your answer, it's sort of like, there's not like a gut feeling, oh, that felt like that's the right answer. You sort of feel like you're just putting something random into the calculator and calculating that. Sometimes I like the actual equation better because it makes sense that the 0.8, that's your chances of getting that seed to grow. The 0.2, 3 of them can't grow, so you can see the 7 growing and the 3 not growing. And the 10 choose 7, that number in front, is all the different possibilities. If you had your 10 plants in a row, well, the 3 dead ones could be the first 3. Or the dead one could be the second one, the 8th one, and the 10th one. And all those different possibilities, all those different combinations get chosen in that 10 choose 7. So what is the probability that more than 8 seeds do germinate? Well, here's where you could use the binomial CDF. You could figure out this binomial CDF of 10, 0.8, and 8 will calculate all the probabilities of 0, 1, 2, 3, 4, 5, 6, 7, and 8 all added up together.
Hello there.
Hello?
I'm sorry for interrupting, Mr. J.
So if you subtracted, adding all of those up from 0 up to 8, what you would be left with is just 9 and 10. So that's using binomial CDF. This one, there is only 2 cases. There's exactly 9 and there's exactly 10. So if you wanted to figure each of them out separately, if that made more sense to you, and then add those cases up, you'll get exactly the same answer. The mean of binomial distribution is quite easy to figure out. If you were guessing on a multiple choice test and there was 40 questions and you guessed on every single one, what would you expect to get right? How many out of the 40? What would your gut say that you would? 10. right? Because you have a 1 in 4 chance, and you have 40 questions, and so your chances of getting a certain amount right would be a quarter of 40, which would be 10. And that's exactly what the formula for the mean is. Just how many trials. Our n here is a number of trials and your p is your probability of success. So yes, 40 questions, you guessed on all of them, you'd expect to get 10 right. Teacher decides to put a 5th option on each one. Now you have a 1 in 5th chance. So if you did 40 questions, you'd expect to get 8 right. That's not to say that you couldn't get more or less, and we could make a probability distribution going from 0 right all the way to 40 right. It'd be a long chart. And look at all those probabilities. But of all those probabilities, that would be the one that would be the most likely. Variance is a measure of how far things are away from the average. So data that varies more is more spread out, and data that varies less is less spread out. Now, anytime you have a binomial distribution, there's a very simple formula for the variance. It's just your number of trials times your probability of success times your probability of failure, which is 1 minus p. We're going to learn more about standard deviation when we do normal distributions. Standard deviation is another way of measuring how much things vary. In fact, it's just the square root of the variance. Notice in this formula, this 1 minus p, we wrote as q before to be what doesn't happen. So that's exactly the same formula, just with a square root sign around it. And I checked your formula sheet, and the variance formula is on there. So you have to know that standard deviation is the square root of the variance, because that isn't on your formula sheet. So this question is very similar to our binomial questions from before. The only thing after is we've added in part B and C, finding the mean and the standard deviation. So part A is just like the first question that we did. You have 50 trials. Your probability of success is 2 out of 7. So we could either use our binomial PDF, 50 trials, probability of success of 2/7, and we want to find exactly 10. Notice here when we get our answer for the 3 sig figs that this 0 doesn't count as a significant figure. So it doesn't mean that you're just going to 3 decimal places. You still need to go 5, 3, 2 for 3 significant figures. And I was curious, if I used the formula, at what point would some of these numbers get so big would the calculator not be able to calculate it? Because 50 choose 10 is a very big number. Doing 5/7 to the power 40 is a very big number for your calculator to calculate. But the graphing calculator was still able to do all of those calculations. Which is interesting because there are some times where certain formulas, if you would plug it into your calculator in this form with the exponents, your calculator might overflow and not be able to do the data. But if you type it in a different way, because of how the calculator's been programmed to figure things out, it can figure out things one way but not another way. So I was curious if this one would cause it to crash, but both formulas still work. So then for a mean, well, it's just our number of trials times our probability of success. We have 50 trials, 2/7 of success. We could expect to get 14.3 blue marbles. And finally, our standard deviations. So if you found your variance formula on your formula sheet, you would know that you would need to take the square root of it. Our number of trials is 50. Probability of success is 2/7. Our probability of failure is 5/7. So our standard deviation in this case is 3.19. And that 3.19 doesn't mean a lot to you yet because we haven't dealt with standard deviations. But what it's telling us is that if we would do this experiment, the mean is 14.3. If you go up 3 and down 3 from 14.3, that would be a range of about 11 to 17. You would expect statistically that about 68%, if everybody did this experiment in this class, and you drew marbles out of the bag 50 times, and we looked at the results, not everybody would get 14. Some people would get 13. Some people might get 18. If you looked at those results, what the standard deviation is telling us is that we could expect about 68% of this class would probably get somewhere between 11 and 17. If you would go 2 standard deviations above and 2 standard deviations below, so if we subtracted 6 to about 8 and we added 6 to about 20, I would expect if you guys all did this experiment, 95% of you would get between 8 and 20. And if you go one more standard deviation out after that, so another 3 down to 5, and another 3 up to 23, statistics will say that that's about 99.7%. It would be really, really rare to do this experiment 50 times and get more than 23 or worse than 5. Yes? We're going to find that, we're going to learn these numbers. It's actually from something that's sometimes called the 68, 95, 99.7 rule. In that when you do a probability distribution and its standard deviation, that the probabilities one standard deviation away from the mean will always be 68% of the data. And if you go 2 standard deviations away from the mean, you will get 95% of the data. And 3 standard deviations is 99.7. So when we look in our normal distributions in the next part, we'll learn more about that.